almost full. And when he put a few more pennies in, it was so full, he decided he was going to get all the pennies out and find out how many there were. So he opened up the bank and dumped out the pennies until he got them all out. And then, when they all came out, he counted the pennies. 1, 2, 3, 4, and it was very hard to count, but he finally counted them all, and he found out that there were, do you know how many there were? There were 515 pennies. Well, after he counted all the pennies, and he was sure he had 515 pennies, he decided that he would like to save nickels. So he thought he would exchange the pennies for nickels. How many nickels would he get for the 515 pennies? How could you figure that out? What would you do? Suppose you didn't have the pennies there and you wanted to figure it out ahead of time. How would you find out how many nickels he could get for 515 pennies? What would you do?
Divide.
I wonder how you would do it. Could you show us on the board? All right. All right, use that. Right up there. 515 pennies. 515. And what does that mean?
5 divided into 515.
Yes, or how many 5s in 515? Now I'd like you all to copy that example on your paper. All right, you go back to your seat now, and we'll work it out our seats. Some of the children showed they didn't really understand division computation when they worked out the problem this way. We asked one child how he worked this example. He said, 5s in 5, 1. 5s in 15, 3. We asked, what's your answer? He said, 13. He had already learned to work through an algorithm mechanically without thinking about the reasonableness of the answer. Now we asked another child how she did her example, and she said, 100 times 5 is 500, so I wrote 1. That left 15. And there are 3 5s in 15, so I wrote 3. Then what is your answer, we asked. Uh-oh, she said, there's something wrong. This child was thinking correctly, but she had trouble with the mechanics of the notation. Why did these children have difficulty? Probably because they were introduced to a formal computation procedure too soon. Apparently, these children didn't really understand the algorithm they had been taught. A good way to begin to build understanding of an algorithm, that is a computation procedure, is to help children work out their own method of written computation. Suppose we start with a simpler problem. Let's say we wish to exchange 65 pennies for nickels. We'll assume that the children haven't yet learned a division algorithm, but that they do know the basic multiplication facts, at least through 10 times 5. The question might be expressed this way. 65 is how many 5s? Here we have a missing factor. Recall that the product divided by the given factor is the missing factor. In this case, it's the quotient of 65 and 5. One way to find the missing factor is to use the repeated subtraction interpretation of division. For this equation, we would subtract 5 as many times as we could from 65 to reach 0. Subtract 5 once, we get 60. Subtract 5 once again. Subtract 5 again, and so on. This procedure can be continued until we reach 0. Then we can count to find out how many 5s have been subtracted. But children are sure to object to this procedure. It takes too long. Someone may then suggest subtracting 10 times 5 or 50 to save time. Then this notation would look like this. We subtract 50, that's 10 times 5, but we still have 15. Someone then suggests subtracting 3 more 5s. So we subtract 3 5s, or 15, and now we have reached 0. We kept a record of the number of 5s here on the side. We have 10 5s and 3 5s, or 13 5s. Applied to the problem, that means we considered as 50 pennies and 15 pennies. For 50 pennies, we get 10 nickels. For 15 pennies, 3 nickels. That's 10 plus 3, or 13 nickels. When this is written this way, you can recognize an application of the distributive property. This condensed procedure that we use for repeated subtraction is a division algorithm. It is a method for finding the standard name for a quotient. Now let's explore another way of introducing an algorithm for division. Ask children a question like, how many 3s in 14? Then ask them to draw an array showing 14 elements with 3 in each row. Of course, they can't do it, because no whole number times 3 is 14. This is as far as they could go. This particular arrangement serves to reveal several important ideas. For example, it shows that the greatest number of 3s in 14 is 4. We have a 4 by 3 array with 2 elements left over. This means that the greatest multiple of 3 less than 14 is 12. And that 14 is 4 times 3 plus 2. The number of elements in the incomplete row of this arrangement is referred to as the remainder. So the remainder in this case is 2. The next step might be to have children solve equations like this, where there is a place to indicate a remainder. And children can use their knowledge of multiplication and addition instead of working with objects or pictures. Let's see how this might be done with a 3rd grade class. Now, we've just seen that there are many ways of solving this equation. We can use 0 or 1 or 2 or 3 for the square, and each time we use a different number for the triangle. Now this time we're going to try a different equation, and we're going to try something different with it. Watch. What number times 4 plus another number equals, ready? But this time, we want to find the largest possible number we can use for the square to make this a true statement. What was our requirement? That we have the largest possible number for the square.
Oh, no.
Okay.
6 times 6.
You see a larger number you could use? Want to try it? Let's try it out. 6 times 4. How much is that?
24.
Plus 3.
27.
It works?
Yeah.
Anybody find a larger number that would work for the square? What would happen if you used 7?
It would be 28. You should right there. Then it would be 28.
Too much? All right. Now we're going to try a different one, and I think, thank you, I think we'd better try one that's a little harder. That maybe was too easy for you. Ready? What number times 3 plus another number is equal to, and once again, we want the largest possible number for the square. That might seem like well, that number may seem to be too big to think about. How would you do it? What would you do?
You'd put in parts.
You mean you do a part at a time?
Yeah.
Well, what part would you do first?
Well, I would take 10 times 3.
Why would you pick 10 times 3?
That's the easiest number I think.
Suppose we keep a record of what she's doing here. She wants to find out how many 3's in 65. Now, if you took 10 times 3, how much would that be?
30.
And if we took 30 from 65, what would be left? 35. Can you get any more 3's in 35?
Yes.
How many more?
3. 11 more.
You could take 11 more, all right. How much is 11 3's?
32.
11 3's.
33. 33.
I see. You were safe when you took 10 3's. You knew that was 30. We could have tried 10 again, but we can try 11 also. That's 33. 33 is 11 times 3. Now how many left?
2.
Can we go any further?
No.
I wonder if someone can fill this out now. All right. Do you want to? Come on. All right, let her do it. She worked it out. I guess we'd better test this and see if it's going to work out right. 21 times 3, how much would that be?
63.
And 2 more.
65.
And how did you know it was 21?
Because 10 and 11 is
I see. 10 3's and 11 3's altogether is 21 3's. We have just seen how, with the help of this notation, third graders figured out the greatest number of 3's in 65. They knew that with the remainder of 2, there wouldn't be any more 3's in 65. Notice that this procedure developed from an idea that one child had about doing this example in parts. Well, note that there are many other possibilities for breaking up this example into parts, as the child put it. It's possible to begin by subtracting any number up through 21 threes from 65. For example, some children might think in this manner. If 10 times 3 is 30, then 20 times 3 is twice as much, or 60. And I know that I can subtract at least 20 threes from 65. That leaves 5. One more 3 can be subtracted from 5, and that leaves a remainder of 2. Notice that this computation procedure is similar to the one that we developed for the pennies problem. Recall that in a division example, we have a product, a given factor, and a missing factor. In a division algorithm, the product is referred to as the dividend. In this case, it's 65. The given factor is referred to as the divisor. In this case, the divisor is 5. And when the missing factor is computed, it is referred to as the quotient, which in this case is 13. The numbers added to get the quotient are referred to as partial quotients. The partial quotients here are 10 and 3. Here, there is no remainder, or to put it another way, the remainder is 0. If the remainder is greater than 0, as it is in this case, then the given factor of this product expression is still referred to as the divisor, and the missing factor is still referred to as the quotient in this algorithm. For whole numbers, when the remainder is less than the divisor, the quotient is the greatest number that can be multiplied by the divisor to make this a true statement. Later, when children are working with fractions, they can express the quotient this way, where the remainder is expressed as the numerator of a fraction. After children understand the procedure we have shown here, the notation may be simplified in the following manner. We write 65 divided by 3 this way, using this division symbol. And since the divisor is indicated here on the left, we eliminate the writing of times 3 on the right. Then the equal signs are omitted, and a vertical separating bar may be used, like this. Now we have a computation pattern which looks like a standard form used in many textbooks. There are slight variations of this pattern in different textbooks. When computing with larger numbers, it is usually easier to try multiples of powers of 10 as partial quotients. That is, multiples of 10, 10, 20, 30, and so on, multiples of 100, or multiples of 1,000, depending upon the problem. For example, here, which power of 10 should be considered? 10, 100, or 1,000? Obviously, 1,000 is too large because 1,000 times 27 is 27,000. Perhaps a multiple of 100 would work. Let's watch a 6th grade pupil who is thoroughly familiar with this algorithm explain how he selects partial quotients in working out this example. Tom, will you explain how you work out a division example like this?
Well, first of all, I'd look at the problem and ask myself what it is. And what this problem is you try and find out what times 27 equals 6,475. And so first of all, I try 100. You want me to use chalk?
What would happen then? Yeah.
Okay.
You write it down. Show me what you're doing, what you're thinking.
And first of all, I try 100 times 27, and that's 2,700, and that's not enough, so I'll try 200. And 200 times 27 equals 5,400, and that's just about enough, so I'll try that. So.
Where do you keep a record of this 200?
Right over here.
I see.
And then you subtract. And so then you try and what times 27 equals 1,075.
I see.
And so, well, 27 is close to 30, so I'll call that 30 for now. And 1,075 is close to just 1,000. Mm-hmm. And 30 times 30 equals 900, and that's close to 1,000, so I'll try 30.
Right.
And 0 times 27 is 0. 3 times 7 is 21 tens.
Now that's
3 tens.
Yes, I see.
Yeah.
Mm-hmm.
3 tens times 7 is 21 tens, so put down 1. Yeah, remember the 200s.
I see.
And 3 tens times 2 tens is 600, plus the 200s from before.
That you remembered, I see.
Yeah, equals 800. So you subtract it.
You still have that much
Yeah.
to divide, I see.
So first I'll try 10, and 10 times 27 is 270. And that's only 5 too much, so I'll try 9. And 9 times 7 is 63. Down 3. You carry the 6 tens. Remember the 6 tens. And 9 times 2 is 18 tens plus 6 tens equals 24 tens. And then you add your partial quotients.
What do you get?
239. So
Now, what does this tell you?
well, 239 times 27 plus 22 equals 6,475.
I see. Do you see any particular advantage in this method that you've used?
Well, if I say I'd only put 100 here, I could still figure it out without having to erase.
I see. This algorithm, as we have just seen, is easy to understand and easy to explain. And although it is adequate for ordinary division computation, children may also be taught a shorter procedure. In some texts, a transition is made to a shorter notation by recording the partial quotients above the bar as shown here. Then, by eliminating some of the notation, we arrive at the traditional algorithm. Here, the reason for each step is not so clear. The child may have been taught to think, how many 27s in 64? About as many as there are 2s in 6. But 3 is too much, so I'll try 2. The fact that this partial quotient must be neither too large nor too small causes some extra difficulty for many children. Notice that here, the partial quotient may be less than 200 without blocking the procedure. That is, if we use 100, we simply subtract 127s twice and get the same result as when 227s are subtracted once. But here, 2 is the only choice that can be made for the hundreds column. And this is the beginning of a cycle which many children memorize and then go through mechanically. Divide, multiply, subtract, compare, bring down. They can go through this routine without being aware that here the digit 2 means 200, or that the 54 here represents 5,400, that the 10 means 1,000 or 1,000, and that the digit 7, that is brought down, stands for 7 tens. The bring down step is really a way of indicating a sum. In this case, 10 hundreds is added to 7 tens to get 107 tens. The whole cycle is then repeated. Divide, multiply, subtract, compare, bring down. One of the reasons, perhaps the main reason, that division computation has been so difficult to teach in the past is that the shorter algorithm was introduced too soon. As a result, it was difficult for children to see how each step was related to finding the quotient. Currently, the tendency is to introduce a more easily understood algorithm, such as this, and to allow children to use this procedure as long as they need to. Children who are especially proficient in computation skills can learn to use shorter algorithms, such as the traditional algorithm. Most children, however, do not seem to benefit from learning a shorter algorithm at least until late in the elementary school. For example, this short division method, where the computation is done mentally and not shown in writing, was once taught in the 4th grade until it was found that it caused children to make too many mistakes. Recall what happened when children used this short algorithm for solving the problem about exchanging pennies for nickels. As teachers, we are more interested in the mathematical understandings which are developed in the process of learning an algorithm than we are in speed and mechanical efficiency in computation. In our discussion of ways of developing division algorithms, we have emphasized the following ideas. First, children can be given opportunities to make up their own algorithms. They can use repeated subtraction to compute a quotient. Second, this process can be condensed by using multiples of powers of 10 as partial quotients. Adding the partial quotients is justified by the distributive property. Third, equations of this type, in which a quotient and a remainder are to be determined, can serve as the basis for developing an algorithm. The algorithm is designed to find a remainder which is less than the divisor. And fourth, the algorithm the child uses should be one he understands thoroughly.